have your attention? Hey, good morning, guys. We're going to move into, with Parker here, training secure web servers for doing vulnerable web servers. So live exploits. So if you can give a round of applause for Parker here.
All right, thank you, everyone. So my title of my talk is A Shell in the HTTP Server Response Factory. Okay, I guess we're doing shells now. We're going to be creating a secure web server from two different vulnerable web servers. And if you don't know what meme I'm referencing, you will see it in a few minutes. Disclaimer, the views expressed by the speaker in this presentation are the same as the official views and positions of my employer. Wait, what? Isn't that usually supposed to say something else? Well, as the founder of the company, Iguana Cyber, I am authorized to speak on behalf of my company. We are still very early pre-seed. All right, about myself. I've spent some time working in both the public and the private sector. I helped contribute to the MITRE Defend framework and CWE when I worked there, and I worked for a major defense contractor. I also have experience as an independent security consultant, helping mostly with penetration testing, and then I tried to figure out, well, how can I stop the stuff that I'm doing? And so this consensus-based defense technique is something that I came up with. All right, let's go ahead. So many people face the problem of trying to determine what program you'd use in a certain scenario. Different programs are going to have different vulnerabilities introduced at different times. So like here we have program 1, it's got a vulnerability from 2023 or so. It lasts like a year. We don't know the severity of it. There's another program. And then, also this had a CloudStrike driver flaw that prevented it from working. Rhymes with a very certain security company that had that same issue earlier this year that grounded hundreds of flights across the country. And then this other program has a vulnerability a longer time. Well, why not all of these? Wait, all the vulnerabilities? Nope, it turns out that we can be secure if at least one of these programs at each given point in time is secure. So like here we see that there's very few times where using all the programs would have been secure, indicated by light green on the left here. But if one of the programs is vulnerable and the others are secure, we're going to show an example of how you could maintain security in your environment. So a quick overview of how this works for a web server. Normal web server, the guy on the assembly line is just like, shell, the HTTP response factory. I guess we're doing shells now. If the intrusion detection system on the host or on the network is not able to detect that what was going on was an exploit, then you're basically stuck. Once you get to the output and it leaves your environment, there's no further filtering that you can do there. The attacker is going to get your private data. But the alternative here is to not listen to that guy and see if we can tell the difference between two different web servers that should be properly responding with the exact same web page content. Now, exact same is caveated by a few different things that we had to filter out for. For example, like obviously the server header in HTTP is going to be different. There's also some other aspects of a web page, like cookies was particularly challenging. And many JavaScript frameworks can, for example, return dictionaries in any order. So that all has to be normalized. But then after we go through that normalization, are these two exactly equal or not? So now you can tell if you got one vulnerable, one not vulnerable web server. Compare these as they're coming off the assembly line, matches up, doesn't match up. We don't need to know what a shell looks like. We just know that it doesn't match up with what's going on right now. We don't rely on any historical baseline. We rely on the actual request on an actual other web server that you set up in your environment. So measure twice, cut once. If just one piece of software is secure against a given exploit, we're able to neutralize these attacks and also prevent data loss. Data loss prevention is a very tough field to do because any number of ways of encrypting or encoding the data the data can get out. A lot of data loss prevention solutions that I've seen are simply fooled by just base64 encoding the data, which, as you know, they should at least be checking for that, right? So in the example here, you send a malicious request. One of them returns the response that the attacker was looking for. The other could be a firewall on the host or whatever. It's not using Linux, so this means absolutely nothing to it. In the middle, our proxy will be able to just send back access denied. So some examples. You have a mission critical binary. Who knows why you're still running something from 2008 and haven't updated it, but it happens in many organizations. Of course, they're not producing any updates for this, but maybe you still have executables for at least Windows and Windows Server, and maybe Linux also. As we're going to see later, if we do the live demo of buffer overflows, the memory layout across operating systems is extremely different. So our buffer overflow techniques are not going to work when we have to simultaneously exploit two different platforms. Or you also know that you have some piece of software in your tech stack that's bound to have a vulnerability, and you want to diversify the risks for that. So now I'm going to step through and see how some of the most high-profile attacks that we might have heard of recently are addressed by a consensus-based defense. So this one's a bit of an older one, Code Red. It's a buffer overflow vulnerability in the IIS web server. But if we were to also add a Linux-based web server, as we had earlier in that backend, the responses that it was sending would not match up. This was a buffer overflow exploit. And so although it may take the Windows web server offline, we would be able to quickly restore it and put another server in place, as I'll show in the third example here. Memory leak attacks. You may also remember about Heartbleed. That was a buffer read overflow. OpenSSL was a library that's widely used on Linux-based systems, not widely used as much on Windows-based systems. So instead, on Windows, the SSL capabilities are built into the operating system. Example, user make wants these 6 letters, potato. The server responds with potato. Another response that should be properly conforming, it requests bird, sends back bird. But now, essentially, what this vulnerability was, user make requests 500 letters, hat. Obviously, the person should not be reading the server's administrator key is changed to this. Isabel wants pages about snakes, but not too long. So now you're able to read information that's private to the server or belongs to other users. All right, so in addition, as I mentioned on our first item about Code Red, if you brick the web server, you're able to stand another one up in its place. So this looks like the logo of a certain security company that rhymes with CrowdStrike that earlier this year took down millions of PCs in the US alone. Instead of we stop breaches, they ended up stopping everything. So yeah, I guess they stopped breaches as well. So we have a cold spare running in the environment. It's usually not used for anything, but it can be booted up and run as needed. Let's see if server B gets taken over by CrowdStrike. We can't boot it. This goes blue screen as soon as we try to do anything and it outside of safe mode. So we can just take that server off the network, however much time we need to respond to it, and then connect to another cold spare, and then there's our 2 subordinate web servers. We still have essentially the same security guarantees as before server B went down. All right, another vulnerability that came about last year in Etsy utils. Basically, many open source software packages had a complete reliance on this one component. A backdoor was inserted deliberately over the course of several years by a GitHub user claiming to be the name Jia Tan, who had no affiliation with other open source software projects or really any information about himself on the internet. However, he was able to convince the maintainers who were overworked into allowing him to get on the software project as an administrator. And then he started making several questionable changes, including inserting an absolute backdoor that allowed anyone with his SSH key access to millions of devices across the internet. So, on Windows, though, instead of the zip utilities being used by that library, Windows uses lz32.dll, so it was not vulnerable. And additionally, if you're behind our proxy or really any good firewall, you're not going to allow port 22 directly to your web servers from an external environment. You're going to restrict where that can be accessed, possibly only internally. And then next, let's talk about speculative execution. So is Spectre still an ongoing problem? I mean, wasn't that so 2018? Is it still something this year? Yes. This past month? Also yes. And this past week? Also yes. So speculative execution exploits, though, however, are extremely targeted to the specific platform, the processor on which you're executing the exploit. For example, Intel, AMD, or Qualcomm, and even more so to the CPU architecture, where instructions on one CPU would mean complete garbage on another CPU. So therefore, using two different CPUs that are using caching the information in completely different ways and use completely different instructions results in at least one backend being unsuccessful. So of course, any responses won't match up and the attacker will not get their sensitive information. So I've mentioned using two different backends, but really what's the historical likelihood of two being vulnerable at the same time? Well, I found using Google's Project Zero, I did some research and found that unpatched vulnerabilities that allowed remote code execution in two web servers, at least, have never occurred simultaneously or within a 2-month window. So if you're able to diversify your other components as well, and use a reasonable patching cycle of at least every 1 or 2 months, then based on this data, you'll likely remain secure, even if there is a simultaneous exploit. As I mentioned, like for example, with the Spectre, you're going to have a hard time matching it up, and we're going to see exactly how a memory leak vulnerability is thwarted with this later in part 2 of our presentation. So today's practice, simple request response. Instead, what we're moving to here is to send the requests to 2 separate web servers, then normalize and compare the responses. If they don't match up, the point here is that we can send a high fidelity alert to the SIEM that something was up. Normally these responses should always be the same so that we know that a successful exploit was attempted against us rather than something general that might not apply to our environment. And this example of it working with WordPress. So if we're able to block these requests that do not, that were obviously an attack, then how effective is it? Well, a 2023 report by Census found that even blocking simple fingerprints of scans, they were able to block 93% of follow-on attacks. The number of targeted attacks goes down to 7% of what it otherwise would have been. And additionally, a report from Hacker Factor last year showed that within the past 10 years, by employing more advanced fingerprint blocking, they were able to reduce themselves to only dealing with one targeted attack and significantly reduce the amount of alerts that their small SOC was able to look at. So in the early days of security, the 1990s and 2000s, we were focused on prevention. Now with things such as Zero Trust, we're focusing more on detection and doing more threat hunting as well. This takes us another level to be able to do some successful prevention. The attacks may still technically occur on the back end to completion, but the data is not going to get out to the attacker. Every attack has to occur in at least 3 phases: the input of the data, the processing of the data, and the output of the data. So if all of the other defenses fail, this will stop the attack when it's trying to output the data in the middle of the proxy right here. All right, so now we get to do some hands-on exploit development, and I'll get into that demonstration I was talking about. I'm going to pull up a Slido link for us so that we can participate along with the questions right here. As well as switch my presenter view, so just give it about 60 seconds right here. All right, so go to slido.com. And we're going to enter the code overflow. It is overflow, O-V-E-R-F-L-O-W. And I will put up a sample question here. All right, so let's get started with examining exactly how many buffer overflow exploits work in a program. To understand that, we're first going to have to look at what memory is read or written to by a buffer overflow exploit. All modern operating systems use a concept called a stack. So let's look at how that works first, as well as a layout of memory inside the stack. Modern programs consist of many different memory segments. These segments include the code, data that's initialized prior to the program being run, and space that's saved for dynamically allocated data once the program has been run, both of a known size or an unknown size. I've included a program if you want to copy my slides, use git clone https://github.com/Parker Garrison/overflow. So this segment memory program, let's take a look at it. It's just going to print out what some segment addresses are on Linux. As I mentioned here, this where the code is stored, this is actually going to be a pointer to the main function here. It's called the tet segment for historical reasons. Then we can look at the initialized and uninitialized data segments here. That's data, and that stands for a block started by symbol. And then the heap and the stack. The stack is where we're going to be focusing our efforts on in the exploits. Because some security relevant information is on the stack, as well as variables that we can control. So if we're not restricted from writing to the bounds of those variables on the stack, then we can overwrite that security relevant information, which is called the saved instruction pointer. So let's take a look at some of these addresses. Let's gcc segment memory.c output segment mem. And then let's run segment mem. All right, so that works here. We get an address in the stack. As we can see, that's near at the high end of memory, and the way our compiler worked, everything else was shoved into the lower memory. And so now let's enable ASLR. On Linux, this can be done pretty much without a restart. And run our program again. Made a typo here, want to pipe that. So now we see the address is different. This is a safeguard that will randomize the start of the stack so that we can't simply insert static values that are known in advance. We have to execute some sort of memory leak in order to get the addresses that we want. So this will all make more sense as we're going through the exploits. So here is that virtual memory layout from the output of our program, just taken and put into here. We have that tet segment, data segment, initialized and uninitialized data, the heap, which we're not going to be touching today, and then memory that can be shared between the stack and the heap as needed. Kernel memory is above all of this, and we're also not going to be interacting directly with the kernel today. We can do our exploits just with user space. And you can see what permissions are typically applied to each of these memory segments, whether they're readable, writable, executable. The only one that should be executable is the tet segment. Though also, if you know the addresses of something in the stack and you can make that executable, then you could write your code in the stack and execute it. That's also more advanced, and we won't be getting to that today. We will just be using an address that we know is in the tet segment. All right, so we talked about ASLR. So now let's go and see, why do we use a stack? Why is this common among basically every platform today? So in the very early days of programming languages, like in the 1960s or so, space for the variables had to be allocated statically before the program was run. When you're dealing with a maximum of 64K of memory, that kind of makes sense. But as we wanted to make programs be able to be more dynamic, and we could include large libraries without saving place for all the variables for the functions we're never going to run, a common idea of a stack came about, in which when we called another function, it reserves place for the variables, and then keep a pointer back to the function stack frames under it, so that when we finish that function, we know where exactly we have to go back to and can continue executing. A stack frame also allows the use of recursion. We can call the same function multiple times without having to rely on the same variable spaces. And this is common to basically every programming language today. So when we call a function, there's some important data that's saved to the stack I mentioned. where we go back to once the program is done. So now we're going to look at the actual assembly language to see how that takes place. The caller is responsible for some stuff before the new function, then the callee, the function that's called, has to do some setup, and then the callee has to actually determine where to go back to in the caller, and then the caller just continues from there, doesn't have to do anything else. So in 32-bit assembly language, EIP is the register that stores the instruction pointer. It can't be changed directly, though when you call a function, the instruction pointer will point to the start of that function. And I also mentioned the stack pointer and the base pointer. So we saw if we go back like to here, the stack is growing downward. Higher memory addresses are at the top of this diagram, and lower memory addresses, where we saw the text segment was and such, are at the bottom of the diagram. So as we create a stack frame for a function that we call, it's going to have a lower memory address. The stack grows towards lower memory addresses and it shrinks towards higher memory addresses. This can sound confusing at first, but some of this was just done for historical reasons. And the reason that the stack grows towards lower memory addresses, but most buffers are written towards higher memory addresses, is why we can overwrite the data of previous stack frames and data that's important to our stack frame. If the buffer was to, say, go in the other direction, then we would only be able to overwrite variables in our local function and may not be able to have as much of an impact. But because of this decision, this is what has made stack-based buffer overflow exploits so common. And now let's take a look at just 3 assembly instructions: push, pop, and call. So pushing a register to the stack, it moves to where the stack frame is at. That's dereferencing the stack address, and that's referencing the stack address, puts that onto the stack, and then subtracts to make more room for the stack. Remember, as the stack grows, it grows towards lower memory addresses. So the edge of our stack is going down towards lower memory addresses because we made more room. If we can also pop something into a certain register, so that will basically take it off the stack, move it back up. Very early assembly languages for early computers, there weren't many other instructions to reference somewhere in the middle of the stack, and so these instructions were used extensively. Nowadays, you'll see them mostly just for setting up and tearing down the start and end of a function. And then finally, to call a function name, this is not an actual assembly instruction, but essentially what it does is it pushes the instruction pointer to the stack and then jumps to the start of that function name. So when we push the instruction pointer to the stack, of course, we are, say, writing it here, decreasing the address of our stack so the stack can grow downwards. All right, so now I want to see how well I've been describing this stuff so far. Let's take a look at the Slido poll if you pulled it up. In a typical program execution, what is the value of the ESP register, the stack pointer, that is the edge of the stack, compared to EBP, the base of the current function stack frame? Is ESP less than or equal to EBP, greater than or equal to, or does it vary depending on the circumstances? All right, I see we've got a lot of responses in already. It was a mixed bag before. I saw one response under each, but now most people are picking the correct answer. We've gotten 70% for less than or equal to. The stack does grow downwards. So now let's take a look at what happens in the called function itself. It will push the base pointer onto the stack, so then the stack grows downwards. Then it will set the edge of the stack to where the base pointer is, and then it will make room for the current variable. So the ESP value will be lower than the EP value by n, whatever amount of space was decided in advance it needs for the variables. Then at the end, it just does the same thing in opposite. Though if the value that it's overwriting at the base of the stack is not legitimate save base pointer, or if the value that was saved right on top of that was not legitimate instruction pointer, then we can take control of the program. So an example here, and the stack, I've reversed the direction of the diagram from before. Lower memory addresses are going to be at the top, and higher addresses are going to be at the bottom. So let's say that works out normally. Now I buffer overflow. And variables, one of them gets overwritten. And then the control goes to somewhere that doesn't exist, because ASCII value AAA corresponds to 41414141, which is not a valid memory address. So we could either determine exactly what the offset is, or we can just start shoving in data and see that's unique per each 4-byte value, and see what exactly ends up in the instruction pointer and the base pointer to see where we can take control of it. So our exploit writing procedure is going to look something like this. We find an input opportunity to write the data. We have to identify what exploit mitigations are in place. And for this talk, we're going to go very quick, so we're not going to implement many exploit mitigations. Then see if we can get the program to crash. So let's take a look at our program that we're going to try to exploit. Instead of having a full-fledged web server also as well, I took out well over 90% of the proxy logic that was dedicated to HTTP, so we can just do this quick demo with an example program I have right here. So let's compile our Wisdom program. We can see already there's some vulnerable functions in here. Gets, that is in fact one that we're going to use. So let's go in wisdom.out, main menu, log in, log out, status, receive wisdom, add wisdom. So add wisdom sounds like a place to enter data. Login does too. Let's see what receive wisdom does first. Don't drink coffee past 4 p.m. unless you want to stay awake until the a.m. A great shell to use is bin bash. You can get a power-up in some video games by entering the Konami code. Okay, well, let's try to add wisdom now. Let's do test 1, test 2. And let's receive that back. Okay, so prints it back to the screen, test 2 right there. We don't know what happened with the string test 1. So now let's try adding some longer data. Let's just hold down the A key repeatedly. And see if we have overflowed that buffer. Segmentation fault. So segmentation fault means that it's trying to access memory that really did not exist. All right, now let's try to figure out exactly how far our offset is into the exploit. So let's use GDB so that it will stop the program and give us what's going wrong. And let's run. Now I have a tool here to generate characters that will that are different every 4 bytes in the overflow directory. If you clone that from GitHub, it's called patgen, pattern generate. So we'll just generate about 200 characters. Should be enough based on the amount of A's we did. So we're going to add wisdom. Let's just put that in both fields. All right, so program received signal 6F, segmentation fault. This is promising right here because that looks like ASCII data. So now let's see what the offset in that pattern was. All right, so we get 2 different values here. What's the difference between little and big endian? Well, obviously we didn't generate that many characters. Little endian and big endian are 2 different ways of storing values in memory. So for historical reasons, Intel decided it was easier to store certain values in memory backwards. So with the most significant byte being the last, whereas other processors were using the most significant byte first. Really, as long as you're reading in a consistent way, both of them work. Though this way that seems like us to be backwards is the one that is more common in processors today. So the name Little versus Big Endian came from the book Gulliver's Travels. It was basically a pointless dispute between two different factions, and so you crack the egg on the bigger end or the little end. Both of them work, but obviously you can't do both at the same time. So we see that we need to pad with 152 bytes of filler before we get to what we want to overwrite our value with here. So if we were to look at the list of functions in this program, see what could we just use in here to overwrite with, and let's just do continue. It's pulling up the library functions, so let's see which function might be valuable to us. Frame dummy, write secret. Oh, shell. Well, maybe if this is in the program, can we just call a shell immediately? I don't know, let's try it. So I've included a script here also, run escape, that will escape the characters so we don't have to write out separate scripts each time. So like, if I will do run escape.sh, and then I'll do wisdom.out. I'm in the wrong directory, I guess. Yeah, move up. So overflow / run escape.sh, wisdom.out. So I'm going to need to first generate 152 A's and then put this value packed in little endian, which I said earlier just means reversing the bytes. So let's get ourselves 152 bytes of filler. And then start making our exploit here. Doing this on the fly without even writing a separate script for it. So if you use a library like PwnTools, then you can pack it into 4 bytes without having to do this reversing manually. Now let's enter some wisdom. All right, hit the wrong key. All right, so what happened here? We called the shell function, or did we? Let's see. The shells may not give a pound prompt back if they work. Oh, broken pipe. All right. Well, if we were able to do this correctly, we would see that we are getting a shell here. So let's try one more thing, just writing it in its own program to print this out. So this live demo has worked 2 out of 3 times before today. So today might be 2 out of 4. We'll see if we can make it 3 out of 4. So A's equals A times 152. And then instruction pointer to overwrite equals shell over here, 9D, 1240. I'm going to navigate the menu. We're going to print 5, and then we're going to select adding wisdom. Exploit is A's plus EIP, and then we're going to print the exploit for both the title and the value of the wisdom. So let's see if we can pipe this in properly, and then let's do python exploit1.py and see if it's printing out exactly what we want. Put it into a hex dump. And yeah, it sure looks like it. Though there is this shell over here. There's an extra C2 character. so let's go and dump this into the wisdom binary. So it did something there, it didn't crash the program. All right, let's try running this in GDB and see what happens. So we will do our run with escape, wisdom.out. So let's quit out of here. We can attach GDB to an existing process. And then continue it. You see if we can do anything over here. Then we didn't attach the right process, so quit out. So now we have no other processes running over here. We should find the right one. And now if we do something here, we see we're hooked to the debugger. Can't do anything. Continue. Now let's enter a title. Let's enter our exploit over here. And since, let's just run this as being escaped, so we don't escape the values twice. Let's continue over here. All right, segmentation fault. So it doesn't like that this value 40129D. So let's examine what's there as an instruction. Can't access the memory. Oh, probably because ASLR is still on here. So it's going to load at a different address. So yeah, ASLR caused it to kick to that different address. So we can see one of our exploits was causing this problem. So it looks like I got like 3 minutes or so to wrap up. Let's see if we can remember to disable ASLR before the demo. And let's run this program again. Attach to it with GDB. And continue. Now let's try our exploit once again. Detaching after vfork from child process. What? So something happened here with our exploit. Maybe the shell creates a child process? Wow, we have a shell. All right, so now I'm going to just show how, if you have a consensus-based defense in place, that this would not work. The other side would crash, and you would have essentially as you'd be accessing memory that didn't exist in the other program, as I was trying to do when ASLR was on in the system. Even if it's on one, but not on the other, then it still won't work. So in this window, we're going to start our binary to run wisdom forever. And then here we're going to run our proxy forever. and then see if we can connect to it. And all right, looks like we're having some timeout errors. All right, well, it looks like I am out of time here, but the point is, if we were able to connect to both systems within time, that the memory addresses would not line up if we were to attempt a memory leak, or if we were to attempt a buffer overflow like this. So even though there was a shell in one system, the response would not get passed through the proxy back to the endpoint of the attacker. All right, I'll leave my contact information up here if you're interested in talking about beta testing this. We are also looking for potential seed investors as well. So I am Parker at parkergarrison.com. And thank you all.